Hey everyone, it's Mr. Wolfe here, and in this video I'm going to be going over hang time. So let's say that you jumped and you were able to find your vertical height, and the one that we did in class was just an example of, let's say you jumped zero point 0.3 meters up in the air. We want to figure out how long were you in the air for. So that means how long, when we're talking about hang time, that's going to be the time up plus your time down. So before we get to the calculations, let's just go about describing this motion. We can do it in multiple ways. Let's first start off with a motion map. I'm going to draw the ground. That could also be like the surface of your palm if you're throwing a ball up in the air. And I'm going to draw, and so hang time, it's this like the split second that that object goes up into the air. So I'm going to make my motion map. And as time increases, the distance that my object's traveling is decreasing. All right, the only reason I'm just bringing this over to the right is just so I don't mess things up kind of going downwards. Like it's easier to see, right? There's not a bunch of overlapping here. But this ball could be just going straight up and straight down. And it's going to increase speed going down. Right. So let's do our velocity arrows first. Right, so big arrow going up, and then it starts to decrease speed. It's still going in the positive direction. It's just decreasing speed. And then at the very top, it's going to be 0 meters per second at the apex. So I could write at the apex, my velocity is going to be 0 meters per second. And that going up, my velocity is decreasing as well. All right. A few other things is that we're going to start increasing speed going downwards now. So my arrows are now going in the negative direction, and they're getting bigger and bigger. So obviously this ball doesn't go into the ground, but I could draw my velocity going into the ground or into your palm because it's not showing where the ball is. It's just kind of representing how big the velocity is at that point. All right. And one other thing we need to do is draw our acceleration vectors. So you always have the force of gravity acting on this object, and it's always going downwards, and it's always a constant force of gravity. That's why my blue arrows are always, at least I'm trying to make them, exactly the same. So my acceleration on the way up is always going to be that negative 9.8 meters per second. Okay. And even at the very top, you still have an acceleration. It's not like gravity ever shuts off. So we have negative 9.8 meters per second, even at the very apex. Your velocity just happens to be 0. That's it. Right. And then that acceleration continues, always acting on that object because gravity really never shuts off. And that's what causes this object to increase speed once it is at the top of its peak, because my acceleration and velocity vectors are going in the same direction. So going down, my velocity is increasing speed, and my acceleration is still negative 9.8 meters per second. And then let's look at my change in distance. On the way up, and by the way, let's make a motion, not a motion map. Let's graph this out. So for a position versus time graph, remember the slope of this graph is my velocity. So as time increases, at least going up, my slope decreases, so my velocity is decreasing. And then on the way down, as time increases, my slope starts to increase because my velocity is increasing. So on the way up, I start from a position here and I go up to the top. And so that's a change in distance of positive, because I'm going upwards, right? 0.3 meters. And then on the way down, I started up top and now I'm going downwards. My distance is still 0.3 meters. I'm just going in the negative direction now. So, and just as a reminder, my slope, units of my slope are going to be meters per second here. So my slope equals my velocity for a position versus time graph. So now let's look at a velocity versus time graph. When you throw the ball up, it has a ton of velocity, right? And it just left your hand. So it's going in the positive direction. So at time 0, my velocity is some high positive value. And then as time increases, my velocity starts to decrease. It starts to go towards that x-axis, but it's going to continue to, it's going to increase speed now, but it does so in the negative direction. So my line is just dead straight. Okay. And the units of this graph, or at least for the slope of this graph, are going to be meters per second. So those are the units for my acceleration. So my slope is literally my acceleration for this graph. And notice that it's always constant. And if we were to actually get a number for this, it would be always a constant negative 9.8 meters per second, which is why we always have that, or at least that's one reason, or one way we can look at it in terms of why there's always negative 9.8, negative 9.8, negative 9.8 at every single part of this object's motion. Right, so now we have some of these ideas in mind. Let's try to solve for what's going down. And one rule is that when it comes to trying to find out how long we're in the air for, is that we have in a situation we have two different types of motion, right? We have decreasing speed and increasing speed, and we can really just only throw one equation. Or we could only explore one type of motion at a time. So I could either do an equation for increasing, for going down, or I could do an equation for going up. But I can't do them together. I'm going to do time down, and here's why. We'll see in a sec, because I'm going to show you all the givens I have for the time down. So I'm just solving for time down now. One thing that I like to do is I always like to, even if it's a simple graph, I like to draw it out and just say, okay, I'm solving for this part right here, time down. So I probably should have done this in green, but I can maybe just like box it and circle it. That's what we're solving for right now. And then everything else is going to be in green. All right, so my givens are going to be my initial velocity. Well, if I just cover this up, my initial velocity at the apex is 0 meters per second. I'm not going to say it's at rest, but it is at 0 meters per second, just for a split second. My acceleration due to gravity is still negative 9.8 meters per second. And I know my change in position, or my distance, which is negative 0.3 meters. So if I look at this situation, it's exactly like our free fall problems, right? Where we're holding an object, it's at rest 0 meters per second, and then we drop it. So it's the exact same thing for this case, for the time down. The equation I'm going to use to find the time is going to be delta x is equal to 1/2 at squared plus my initial velocity times time in this case. And the reason why I'm using this equation is because I'm looking for time, and I have all the other variables. I have my initial position, I have my acceleration due to gravity, and I have my change in position. So I'm just going to start to plug in numbers now. Negative 0.3 is equal to 1/2 negative 9.8 times time squared. And then I'm running out of room, but good news is that my initial velocity is 0, so it doesn't matter what my time is. Those things are going to cancel out right there. And then, let's see, if I start to combine some stuff, negative 0.3 is equal to negative 4.9. That's 1/2 times negative 9.8. And then I have my time squared is what I'm looking for. Okay. So then I'm going to divide negative 4.9 by both sides. So it's going to end up being, and then that negative 0.3 divided by negative 4.9 is going to give me a positive 0.06. Just want to make sure of that. Let's put maybe another decimal on it, 0.1 seconds. But that's going to be not time, that's my time squared. So to find my time down, I need to take the square root of both sides. So the square root of that answer is going to be 0.247 seconds. Now remember, this is just for my time down in this case. Right, just for my time down that I solved for. So I'm not done yet. I have not solved for my hang time, just found the time down. So how do we find the time going up then? What do we do for that? Well, it turns out that we have a nice rule, okay? And that rule is that how long it takes you to go up is the exact same amount that it takes you to go down. So if that's the case, if I know my time down, then I just need to multiply it by 2, right? In order to get my full hang time. So the hang time for this problem is just going to be 0.247 times 2, and I'm going to get an answer of a hang time of 0.495 seconds. Now I finally have my answer in this case. And one thing maybe I probably should have done is I'm not solving for this green area anymore, so maybe the hang time I'm just going to go back to in black, because I want that green to show that was just for the time going down. And then I realized I had to multiply it by 2 when I looked at my visual and I said, oh, I've only solved for half of this. So my hang time is 0.495 seconds. One other rule that I want to talk about is that, kind of like how we had a nice rule for the time up is equal to the time down, it turns out that your initial velocity, or your takeoff velocity, is going to be equal to your landing velocity. Now, the only difference is this one's negative, this one's positive, but the number, like if I took off going at 4 meters per second, I'm going to be landing on the ground going 4 meters per second as well. So landing velocity. So that could be another helpful rule when it comes to certain equations. All right. The next example I'm going to go over is... Actually, you know what? I might just make another video, just so this one's not going to be super long. So if you want to see me go over on page 10, number 2, that'll be another video. But thanks for watching this one, guys.